Good day and welcome to the second in the series of STEAM lectures hosted by Project Solutions Limited. Project Solutions are an engineering design and project management company with offices in Yorkshire and Teesside. My name is Brian Lawson, and as well as working for Project Solutions as the technical director, I'm also the chair of the IMechE Western Area Committee. This series of lectures doesn't happen by magic, and there's lots of people helping in the background. So thank you to Nikki Baxter from the IMechE, and also we're collaborating with colleagues in HQ at Birdcage Walk. So thank you to Lucy Edmund's team. We've got Fiona Wong supporting us today with the Workcast platform. We previously run these lectures for the Yorkshire region, and they proved very popular. And that's mainly due to our presenter, Dan Wells, who does a fantastic job, and also the brilliant support that Spirax-Sarco UK give him, delivering continued professional development to engineers around the UK and further afield. We've also got Stephen Bishop, one of Dan's colleagues, helping. He'll be helping manage questions as they come through. If you'd like to ask a question, you just press the Ask a Question button. Can't be much simpler than that, and type something into the chat. We'll probably pool all of those questions and take them as a job lot at the end, but if there's something that would be done while we're live, we will do. The lecture will be recorded and it'll be posted on the IMechE YouTube channel. And it is a shout out for anybody that wants to get more involved with volunteering with the IMechE regional committees. This is for anywhere in the UK. If you follow the links in the IMechE website, you'd be able to get in touch with somebody in your region, because as I say, these things don't happen without somebody doing something, and most of the guys that are making things happen are doing it on a voluntary basis. So please, if you would get involved. Without further ado, I'll hand over to you, Dan. Take it away.
Great. Thank you very much for that introduction, Brian. I'd also like to thank the team at Projects and also the team at IMechE West Yorkshire and IMechE nationally for making today's presentation possible. My name's Dan Wells. I'm the National Consultant Specialist for Spirax-Sarco. And as Brian mentioned, I'm joined on today's presentation with my colleague, Steve Bishop. So please do take advantage of that chat function, and we'll do everything we can to address any questions either as we go through the presentation or once we reach the end of today's presentation. So today's presentation is number 3 in a series of 8 presentations that we've put together to cover different aspects of the wider steam and condensate loop. So last month we started off the series with an introduction to steam systems where we covered the fundamentals and steam generation. 2 weeks ago, we looked at basic steam system design considerations, the good working practice we need to observe in ensuring that the best possible condition of steam arrives at the process. And today, we're going to look at the topic of heat exchange in a little bit more detail. But as you can see, we're going to go through a variety of different topics in the coming weeks and months. Each of these presentations has been recorded and will be uploaded to YouTube. So if you miss any of the presentations in the series, you can easily go back and re-educate yourself on anything you may have missed. But just for the benefit of anyone that hasn't worked with Spirax-Sarco previously, I just want to give a very, very quick overview to who we are. Well, Spirax-Sarco are a FTSE 100 organisation based in the UK. But as you can see, we've got a number of different subsidiary companies, officers and employees in all corners of the globe. As far as here in the UK is concerned, We're a team that's approximately 200 strong, about 50% of which are home-based, so we're always on hand wherever our end-user clients' sites or offices may be. But we also make a number of different resources available to support our clients online. And that can be in the form of a variety of online calculators and configurators and tutorials to educate you with regards to the financial cost of steam, the financial benefit in recovering condensate, and to help you with various designing and sizing considerations. We can even take that one step further, because as you can see by referring up to the little icons in the top right hand side of the screen, we've got the same very, very powerful suite of calculators and configurators that are available to download onto your smartphones. It's a free of charge app. I would encourage you to download that. It will make life very, very easy for you. Whenever you're required to give a very quick and high level appraisal of a steam distribution network, or whenever you may be required to size pipes, control valves, or steam traps, for example. I would encourage you to download the Spirax Sarco Mexico version in preference to the UK and ROI version, as there is a greater series of calculators and configurators, and you can also change the language and change the units back to English again. So on with today's presentation, which, as we've mentioned, is on the topic of heat exchange itself. And what we need to remember is perhaps the single main reason why the vast majority of our clients have steam on their sites in the first place is likely to be for some form of heat exchange requirement. And we need to remind ourselves that when we talk about heat exchange, we're basically talking about the transfer of heat energy from the primary side of the heat exchanger to the secondary side, to the process. It's an exchange of heat without there being an exchange of media. And as you can see on the screen, heat exchangers, well, that terminology can cover a huge range and variety of different capital equipment, such as it can be shell and tube heat exchangers, plate heat exchangers. It can be process capital equipment such as jacketed vessels, bioreactors, coils in air handling units, or even reboilers in the oil and gas industry. So in today's presentation, we're going to look at why steam is so popular in so many different heat transfer applications. And we're also going to look at the considerations that we need to give to steam that are completely different to other sources of heat energy, such as low temperature hot water, for example. And then we're also going to look at other issues that are unique to steam heat exchangers, such as stall and condensate removal. But the first slide I want to show is a slide that I show in a number of the different presentations that I'll be delivering in the series. And that's because it's perhaps the single most important slide. And this really shows us the energy content that is present in a mass of steam and how that can change in accordance with the steam pressure. So if we look first of all over towards the left-hand side of the screen, we can see what we refer to as the steam tables. And we've mentioned in previous presentations that water, the raw ingredient of steam, has got a specific heat capacity of 4.19. In other words, if we want to heat 1 kilogram of water at the process, then we need to ensure that we add 4.19 kilojoules of energy to it just to raise the temperature by 1 degree. So if we want to raise water from 0 degrees to boiling point, which at atmospheric conditions or 0 bar gauge we know is 100 degrees, you can see we need to add 419 kilojoules of energy into it. However, but if we want to make that same kilogram of water move from boiling point, so it then becomes a fully evaporated mass of steam, well, we need to add a further 2,257 kilojoules of energy to it. We call that the latent heat. We can also refer to it as the enthalpy of evaporation. So when that kilogram of water has fully evaporated and produced a kilogram of steam, the energy content is the sum of the two that are shown in this column here. And that now means that we've got dry saturated steam and we understand its energy content. The final column, that shows us the volume that steam has at the given pressure. Now, that could be the pressure that the steam is generated at in the boiler. It could be the pressure that the steam has in the distribution network, or it could be the pressure that the steam exists at in the heat exchanger itself. And if we move across to the temperature enthalpy curve, this shows, or it demonstrates, the journey that water takes as it changes state from a liquid to produce steam as a gas. So if we take the example of 0 bar gauge, where we know water boils at 100 degrees, you can see that water starts to change state to steam. The evaporation process begins, but only when we've added 419 kilojoules of energy to it. The water then continues to evaporate, and the evaporation process only ends when we've added that full enthalpy of evaporation, latent heat energy, into it. So when we've added 2257 kilojoules to 419 kilojoules, we have then got dry saturated steam. And we've mentioned in previous presentations that dry saturated steam is critically important whenever we're sizing heat exchangers or calculating the rate of heat exchange for the process. As we've mentioned, we've got a number of issues caused by steam that is not dry and is not saturated with energy. In other words, with wet steam. For one, it's more likely to condense out in the distribution pipework. And the more heat loss we've got in the distribution pipework, the more condensate we've got generated. And that means that it could well be that we've got a starvation of steam available for the process. For example, if the heat exchanger requires 9,800 kilograms per hour, if we're producing 10,000 kilograms per hour in the boiler, but if we're losing 500 kilograms per hour to the distribution network, then we simply may not have enough steam available to satisfy the process. We've got the other issues we've spoken about previously. Wet steam, more condensate. If we've got more condensate, we need to install and maintain a greater number of steam traps, and we're exposing ourselves to a greater risk of that erosion, corrosion, and water hammer that we've spoken about previously. But that steam that's passing across a trapped film of condensate in the bottom of the pipework, it's going to have its energy level further degraded. So we get a greatly reduced mass of steam finding its way to the process. But the steam that does manage to find its way to the process, it's going to have less energy contained within it as well. So you can appreciate that wet steam is by far and away one of the biggest problems that we can encounter whenever we're talking about using steam for heat exchange purposes. All of the steam tables, all of the calculations we make are based on the assumption that that steam is going to be dry saturated steam. If it's wet steam, then all bets are off. So aside from that high energy content that steam has compared to water, we've mentioned in previous presentations, a kilogram of steam's got approximately 50 times more heat energy contained within it than a kilogram of water, especially if that water is only designed to give up a certain range, a certain amount of temperature at the process. So if we've got a water-to-water heat exchange working on an 11-degree delta T, a kilogram of steam will have 50 times more energy contained within it. So, of course, there's a huge benefit there for our client. They need to generate and distribute far, far less steam. But it also means if we've got more heat energy contained within the steam, the heat exchanger can be smaller compared to a water-to-water heat exchanger. But we also know that steam gives up its heat energy equally and evenly across the entire heat transfer surface area. And we're trying to demonstrate that in the little picture that you can see up in the top right of the screen. It's a sauna. Well, if we put 2 or 3 kilograms of steam into a sauna, as a gas, it's going to spread out and it's going to occupy all of the heat transfer space. But if we put 2 or 3 kilograms of water into the sauna, it'll just sit there in the bottom of the sauna as a puddle. It's not using that heat transfer space very efficiently at all. So that uniform exchange of heat energy means that we're less susceptible to getting striations and cold spots in the heat exchanger if we're using steam compared to using water as the primary source of heat energy. That's yet another reason why we need smaller heat exchangers if we're using steam compared to water. And another critical benefit of using steam compared to water as the primary source of heat energy is we need to remember that steam gives up its heat energy by condensing, by changing state from gas to a liquid. And that means that the speed of heat transfer, or the heat transfer coefficient, is about 3 times greater than with a water-to-water heat exchanger. So those 3 benefits help us to understand why we only need a smaller heat transfer solution in order to get the heat energy into the process. So just to remind ourselves, when steam's being used to heat a process, it's that enthalpy of evaporation. It's the latent heat. It's the energy that we added to the boiling water. That's the energy that passes from the primary side to the secondary side. And we can only use this latent heat energy, this enthalpy of evaporation, to heat the process. It's approximately 75% of the total heat energy. So that means that the energy that we cannot use, the energy that's left behind, that's retained within the condensate, the liquid, that's about 25% of the total heat energy. We refer to that as the sensible heat. And just as steam's got a direct pressure to temperature relationship that we've spoken about previously, well, so too does that condensate. And I just want to come back to that direct pressure temperature relationship that we've spoken about. The steam saturation curve that we can see above, as we've gone through in previous presentations, it demonstrates that if we know the pressure of the steam, well, we know its temperature. For example, if we're distributing steam in the pipework at 10 bar gauge, the steam saturation curve tells us that the temperature of the steam is 184 degrees. But if we only require a temperature of, let's say, 130 degrees at the process, well, this tells us that we can achieve that temperature by manipulating the pressure down to 2 bar gauge. So that's the first benefit of having that pressure temperature relationship. The second benefit is we know that when steam condenses, it gives up its latent heat energy. There's a change of state. There's an exchange of energy, but there isn't an exchange of temperature. So the condensate that's being distributed, or the steam that's being distributed at 10 bar gauge, the condensate that exists as a result of that heat loss, that condensate is going to exist at 10 bar gauge, 184 degrees. And once we've reduced the pressure of the steam at the process down to 2 bar gauge, 132 degrees, the condensate will exist at the same conditions. It's a different phase, it's a different state, but it will exist with the same pressure temperature relationship. There's just simply far, far less energy contained within it. Now, one way that we can utilize that pressure temperature relationship at the process, at the heat exchanger, it means that we can control the release of heat energy very, very easily by simply using a 2-port valve. Now, it can be a self-acting valve, or it can be a control valve, as we can see in the little image on the screen. Because we need to understand that if we've got a certain temperature requirement in the steam, we can achieve that by nothing more than reducing the pressure. So let's compare that to a water-to-water heat exchanger. Well, we know for one, there's far, far less heat energy contained within the water. We also know that whilst we don't pump steam, steam moves in accordance with the pressure drop. We do need to pump the water. And we also know that any heat energy that isn't required by the process, when we're using a water-to-water heat exchanger, well, we will need to divert that unwanted energy away. So if you compare a steam heat exchanger to a water heat exchanger, we're likely to require a 3-port valve, and we're likely to require a small circulating pump on the skid to allow for that unwanted energy to move away from the process. So it can be more complex a situation or a solution to engineer. So I just want to talk now to show us how all of those key benefits can pull together on one little graphic here. So if we look at the GIF image, well, this really reminds us that one of the first things we want to do is to ensure that the air is vented away from the system, and we can get the air out of a steam using system by simply using the steam pressure to push the air across a thermostatic valve, at which point we can bring the process up to temperature very, very quickly. We also know that steam's got a very, very high energy content and a very high heat transfer coefficient. We sometimes refer to that as a U value, or a speed of heat transfer. And we also know that steam gives up its heat energy at a constant temperature, and it uses all of the heat transfer space evenly, meaning we don't get cold spots or spoilage. And it means we can bring the temperature of the process up to the required set point by nothing more than manipulating the steam pressure. So I want to look at a number of heat transfer equations now, and there are a number of different heat transfer equations, but for the majority of the most popular applications, the above three equations will effectively demonstrate the key elements of heat transfer. So I want to start with the equation at the very top of the screen, and that also applies to the process that we can see at the far right of the screen as well. So for example, if we wanted to understand how much energy was required to bring a particular process up to temperature, then this is the equation that we would use. So we've got an example here whereby we may need to bring water up to a temperature of 90 degrees from a starting point of 70 degrees. Well, we can calculate the energy requirement. That's typically referred to as the Q value, by multiplying the mass flow rate of the process by the specific heat capacity by the temperature rise. Well, the mass flow rate requirement, we can simply get that from the client or from the process owner. They will help us to understand how much media needs to take on that temperature. In the case of the process example we're looking at here, we can see that we're adding energy to water, which we know has got a specific heat capacity of 4.19. And we can see that we need to add 20 degrees temperature to the process. So we simply multiply the mass flow rate by the specific heat capacity, by the temperature, and that helps us to determine the Q value, or the amount of energy we need to add to satisfy the process. So the next equation, which is also demonstrated here in the middle of the P&ID, that tells us how we calculate the rate of heat transfer, the speed of heat transfer. And that's critically important because it helps us to understand how to correctly size the heat exchanger itself. And we can find the heat transfer rate, or the Q value, by multiplying the heat transfer coefficient. That's the U value, the speed at which the energy will move from the primary side to the secondary side. Now, if we're looking at an existing heat exchanger, it's highly likely that that information will be badged on the unit already. If not, we can refer to the manufacturer's thermal energy data sheet. Or if we're sizing a totally new heat exchanger for a new application, we can go back to first principles and we can calculate it from the appropriate sizing charts. We want to then multiply that by the heat transfer surface area of the heat exchanger itself. We refer to that as the A value. Again, that can be badged on the unit itself, or we can take it from a manufacturer's thermal energy data sheet in the case of an existing heat exchanger. But if we're going back to first principles to size a totally new application, then we can do it by means of calculation. And we then multiply that by the temperature difference between the steam on the primary side, which, remember, we can use the steam tables to denote the steam temperature by having an understanding of the pressure, and then we multiply that from the average temperature of the process being heated. So in the case of the equation we're looking at here, the average temperature of the process is going to be 80 degrees. So by multiplying the U value by the A value by the temperature difference, we arrive at the Q value. And then finally, we can use the equation that you can see on the bottom of the screen here, or on the left-hand side of the process flow diagram. We can multiply the mass flow rate of the steam required by the heat exchanger by the latent heat energy, or the enthalpy of evaporation that's present in the steam. Again, we can get that from the steam tables, and that will tell us the amount of heat energy that is required on the primary side of the heat exchanger in order to satisfy the process. Now, what we need to remember here is that if we go back to first principles with thermodynamics, we know that energy in must equal energy out. It cannot be created. So what that basically means is if we've calculated the Q value at any point of the process using the equations you can see here towards the left-hand side of the screen, well, we can simply carry the Q value across from one point to another point. For example, if we've calculated how much energy the process needs, by definition, we've also calculated how much energy needs to be present in the steam on the primary side. Now, we also know that we can transpose the different values in these equations. For example, if we knew the Q value, but we didn't know the mass flow rate, or if at this point here, we knew the U value, but we didn't know the Q value, we can simply transpose the knowns and the unknowns to find out the information that's required. But please remember that all of these equations are based on the understanding that the information we're taking from the steam tables is based on the understanding that we've got an excellent condition of steam. It's dry, and therefore it has the maximum amount of heat energy contained within it. So as far as steam to water heat exchangers are concerned, especially plate heat exchangers, it's that U value, it's that heat transfer coefficient is perhaps the most interesting, as this refers to the speed of heat transfer as it moves across that thermal barrier. And you can see from the chart above that the heat transfer coefficient of steam is about 3 times greater than that of water. So that means we've got a greater U value, and therefore we only need a smaller heat transfer surface area. We need a smaller A value. And that's one of the reasons why steam to water heat exchangers can be far, far smaller in footprint than water to water heat exchangers. And as most plate heat exchangers that are used on steam systems are gasketed as opposed to welded or brazed, this means we can also manipulate that U value by taking the heat exchanger apart for cleaning and moving away any scale or debris that can inhibit the rate of heat transfer. So the benefits of a smaller heat exchanger are that we only require a smaller footprint of space in the plant room. And if we're holding less water in the body of the heat exchanger on the secondary side, we get fewer standing losses. We get less heat radiating out into the plant room. Now, suppose the downside of having a smaller heat transfer space or a smaller A value is we really need to be on top of moving that condensate away. Because we know that condensate, the byproduct of heat exchange, it exists as a liquid. And that liquid condensate, as we know, it's got far, far less heat energy contained within it. So if that condensate is allowed to back up and flood the secondary side, flood the primary side, it means we're going to have a barrier to heat transfer. The heat transfer rate is going to slow down and slow down. So it's at this point I really want to revisit the steam tables. So we know the benefit of generating steam at a higher pressure from previous presentations. At a higher pressure, the steam is far more likely to be drier and have more energy contained within it. We know that it's going to contain a much, much smaller volume, and therefore it's going to be cheaper to distribute that steam in a smaller infrastructure where we get fewer distribution losses. We get a greater efficiency. But the first thing we want to do when we get that steam to the process is we want to reduce the pressure. And we typically do this for 4 reasons. So first of all, it's for process control and efficiency. For example, if we're distributing steam at 10 bar gauge, 184 degrees, but the process only needs, let's say, 165 degrees, then any excess of pressure is going to be an excess of temperature. And that means it can be a problem with regards to not only efficiency, but also quality of the process. Second reason is, well, we may need to protect the heat exchanger from exceeding its maximum working pressure. For example, if the heat exchanger is rated to 10 bar gauge, we're going to have problems if it's exposed to a pressure that is significantly greater. So we need to reduce the pressure for that reason. But the other reasons are slightly less apparent, and they're more apparent by referring to the steam tables. So first of all, we can see that there's more useful heat energy. There's more latent heat present in steam at a lower pressure. So if we take the example of 10 bar gauge, you can see the enthalpy of evaporation, or the latent heat. That's the energy that can be used by the process. It's far, far greater at a lower pressure than it is at a higher pressure. So we've got an increase in efficiency and heat transfer speed by reducing the pressure at the process. And what you'll also see is the opposite's true with the sensible heat, or the enthalpy in the water, the energy that's present in the condensate. If we reduce the steam pressure, we've increased the energy that can be used by the process, and we've reduced the energy that is present in the condensate. Remember, that condensate doesn't have any value to us. So that means as that sensible heat passes across a steam trap and sees a fall in pressure, there's going to be far, far less flash steam being produced. So it's also worth bearing in mind that there's quite a useful rule of thumb that you can bear in mind as well when it comes to understanding the mass of steam required to heat a process, and also the energy content of a mass of steam. And that very, very broad and useful rule of thumb tells us that if we've got a process that requires 1 kilowatt, it needs to be supplied with approximately 1.8 kilograms per hour of steam. And conversely, 1.8 kilograms per hour of steam is capable of providing 1 kilowatt of energy to a process. Now, that information, it doesn't take the place of those calculators and configurators, and it doesn't take the place of going back to first principles and referring to the steam tables. It's just useful as a very, very high level sanity check if ever you're walking into a plant room and trying to get the understanding of what the system requirements may be. So as we've already mentioned earlier, steam gives up its latent heat energy by condensing, by changing state from a gas to a liquid. So above you can see what we refer to as a typical closed loop system, a heat exchanger. And that's when steam goes onto the heat exchanger itself, and that liquid condensate that's full of that sensible heat that we cannot use, it's got to be drained away. So it bears mentioning that steam can be used for direct injection purposes, in which case the steam, and therefore the condensate as well, it becomes consumed by the process or by the atmosphere. So when that's the case, there simply isn't going to be any condensate to remove anyway. The condensate and the sensible heat become part of the process. So an example of a closed loop system, it could be a jacketed vessel, a shell and tube heat exchanger, or even a plate heat exchanger. But I just want to look now at how shell and tube heat exchangers compare with plate heat exchangers. So shell and tube heat exchangers, they can be non-storage or flow type, or they can be storage heat exchangers. So let's consider a traditional shell and tube storage heat exchanger, sometimes referred to as a calorifier. And these are still widely used in a lot of building service applications and also a lot of process applications. And that's largely down to the peace of mind that that huge buffer vessel of hot water can provide. But holding that hot water in storage can bring a lot of challenges for our clients. For example, if we're holding water on the secondary side at a high temperature, it's got to be held under pressure, and therefore it's got to fall under the Pressure Equipment Directive. And if we're holding water at a high temperature, there's a risk of Legionella. It's going to fall under the L8 requirements. So that's going to bring quite a lot of risk and also a lot of inspection and water treatment requirements. But we also know that that buffer vessel is going to be a fixed size. And the little shell and tube, the little heat bundle assembler at this point here, that's also going to be a fixed size. So that's what we refer to as having a fixed A value, a fixed heat transfer surface area value that we looked at on those previous equations. So that means that it's very, very easy, and indeed it's very tempting for any manufacturer to oversize a heat exchanger. They think they're doing the right thing by ensuring that the client has got a constant supply of hot water readily available, but that can bring a number of different problems. So the excellent properties that steam has, the high heat content, the rapid speed of heat transfer, and the fact that we use all of the heat transfer surface area very, very efficiently, it means that we can now generate hot water from steam instantaneously on demand. And that means we can move away from the need to hold hot water in storage. And that brings us a lot of benefits that will go on as we move through the rest of the presentation. So let's look at a typical application, and the application I've chosen here is the generation of hot water for a hospital. Now, it could easily apply to any other building or process that's using hot water. A hospital just happens to be the application that I've chosen here. So whenever we've got a requirement for hot water, we typically refer to that as a draw-off point. And all of these draw-off points can serve a different purpose, and they can all have a different fluctuating demand around site at different parts of the day. So it can be very, very difficult to accurately determine how much hot water is required and therefore how to size the heat exchanger. So we need to be very, very clear about how we've calculated the demand for hot water. And in the case of a storage calorifier or shell and tube heat exchanger, it's got a fixed volume on the secondary side. So we've only got one opportunity to get this sizing correct. So if we're engineering a heat exchanger for a totally new application, could be a new hospital wing, then we can add up the loading units by using sizing formulas such as EN 806. But as we can't accurately estimate peak loads and so forth, it's going to be highly likely that any traditional storage solution is going to end up being oversized. So if we end up with an oversized heat exchanger, not only does it mean that the capital cost is likely to be more than it needs to be, but it means that this heat exchanger is going to be working inefficiently because it's going to be generating more hot water than the site actually needs. So together with the fact that it's going to be taking up more and more space in the plant room itself, and because of this increased mass of steel and the increased mass of water that's held in storage, we've got more radiating losses and standing losses. So if we compare that with a plate heat exchanger that's generating hot water from steam instantly and on demand, we've completely eliminated that risk of oversizing. And it becomes slightly easier if we're looking at removing an old or an existing hot water storage calorifier and then replacing it with a plate heat exchanger, because all we need to do in circumstances such as this is fit a flow meter on the cold makeup. This is going to help us to understand how much hot water is required by the process. So I think perhaps the very, very worst thing we can do if we're looking at replacing a shell and tube heat exchanger with a plate heat exchanger is just replacing the duty like for like, because all we'd be doing is replicating that inefficiency. So old calorifiers, storage systems, such as the one we can see on the screen at the moment, they're going to bring any steam using site a number of different operating issues. It's the storage of hot water that may never be required. So we've got that inefficiency. We've got a further inefficiency because we're going to have a lot of heat energy radiating out into the plant room. We're taking up quite a lot of plant room space that could be set aside for other items of capital equipment or for production purposes. We get a very, very inefficient rate of heat transfer. Why? Well, we get a very inefficient rate of heat transfer because that A value, the heat transfer surface area, is going to be far, far smaller with a tube bundle assembly than it is with a series of plates. That means if we've got a very, very small A value, we need to have a far, far higher U value to satisfy the rate of heat exchange for the process. That in turn means we're likely to need to condense the steam at a far, far higher pressure. And as we know from referring to the steam tables, the higher the pressure of the steam, the less energy there is present within it, and therefore we get a greater inefficiency. So that oversizing, it means that it can be far more susceptible to scaling. If we're distributing steam at a high pressure, that high condensing pressure and temperature means that we're more susceptible to water chemistry creating scaling on the tube bundle assembly itself. That scaling is going to require stripping down and inspection periodically. And that's on top of the pressure equipment directive and the Legionella inspection costs. So we're going to need a significant amount of downtime and manual handling. So we keep mentioning the benefits of efficiency by being able to generate steam from hot water instantaneously. But it's always worth bearing in mind the maintenance, the downtime, the inspection costs, the risks, and the health and safety benefits that a move away from a storage solution to an instantaneous solution can bring. And it's easy to see why so many storage heat exchangers, are oversized at the design stage, because that's when it can be difficult to get accurate and reliable information from the various process owners and stakeholders around site. So if everybody was tempted to add 5% on for resilience, it means that we can generally end up with a heat exchanger that in many cases can be holding up to 3 times more hot water than the site actually requires. So you can appreciate if that were to occur, we'd get a huge footprint of space taken up by the solution in the plant room, a massive radiating loss, and a huge solution to maintain. So I just want to remind us that by moving away from that storage solution towards a typical plate heat exchanger that's generating hot water from steam instantly, we're going to get a significant number of energy saving, cost saving benefits. And part of this goes back to the first principles that we've already covered. Steam's a gas, gives up its heat energy evenly. So we've got an efficient use of the heat transfer surface area by having a greater number of plates. It also means that we've got significantly more heat per kilogram than water. And that means that we need to add all of that latent heat energy to it to make water boil, to change state to steam. And then we've got the high speed of heat transfer, which is steam's got a rate of heat transfer that's approximately 3 times greater than water. So all of these factors mean that we can get away with condensing steam at a much, much lower temperature and therefore at a much lower pressure. And because the steam tables tell us that there's more useful energy in steam at a useful pressure, it means that we're going to enjoy significant cost-saving benefits by moving towards that instantaneous solution. So with regards to controlling the release of energy from the steam into the process, there are a number of different control options that we might also need to give thought to ensure that this energy can be controlled. And that can be asking ourselves questions such as whether we're looking at a batch process or a continuous process, the temperature fluctuations, do we require to send feedback? Is it going to be an intrinsically safe area? Because answers to all of those questions are going to point us in a different direction with regards to whether we're looking at self-acting controls or pneumatically or electrically actuated controls. So with regards to understanding the control philosophy of the heat exchange in a little bit more detail, well, the most basic control of heat transfer is what we refer to as on-off. That's where the valve is either fully open or fully closed and nowhere in between. So it's a bit like turning your lights on at home. You've got the on switch and the off switch. Very, very coarse control, very crude. It's not suitable for every application, as you can probably understand, but we can improve on that by moving towards proportional control. And that's what's commonly featured within a self-acting valve. And that's where the valve opens and closes in proportion to the required temperature change of the process. So example, if the process is only calling for a little bit of energy or a small temperature rise, then the valve's going to open incrementally. So if we're using a tank of water that's using a steam coil to heat it up as an example, if it's got a set point of 60 degrees, that means the valve could start to open at 59 and then start to close at 61. So we'd refer to that as having a 2-degree proportional band. So using the analogy of the light switch, it's a little bit like moving away from the on-off switch to a dimmer switch. It means it's cheap, it's simple, it's easy to engineer, but it's not ideal, as you can see from the little graph in the bottom right of the screen, because certain processes may not be able to live with that 2-degree overshoot, meaning that we get a slightly inconsistent temperature and that the valve could be in a position where it's constantly fighting itself. So that's typically available within self-acting controls. If we want to improve upon that, then we can move towards proportional control that has got integral control added to it. And this is where the valve can then start to predict any required temperature step changes and act accordingly to start to smooth out that little overshoot that we've spoken about. And we can improve on that further still. For example, if we've got a process that's demanding a very, very responsive, efficient and accurate output of water on the process side, then we can move towards proportional, integral and derivative, or P plus I plus D control, to ensure that we get the optimum conditions. So whilst we can only offer proportional control with self-acting valves, that's going to be suitable for large, stable, non-critical processes. For processes that need to respond quickly, accurately, maybe even to send feedback remotely to a BMS or PLC, then we're going to need to upgrade to either an electrically or pneumatically actuated control valve. And it's also important to give thought to the control valve characteristics themselves, namely the design of the plug, the valve seat. And that's because that's going to determine the speed of operation. So typically, we recommend an equal percentage characteristic, as this is going to give us a far better control of the steam. But it also means that the valve will send less time sat close to its seat. Because that, from previous presentations, you'll appreciate that when a valve spends a lot of time operating close to its seat, that's when we're likely to get the abrasive and erosive nature of wet steam really affecting the passage of energy onto the process. And that's when we're going to get an inefficiency, maybe even a nuisance trip out of any high limit valve. So I want to go back to that traditional storage calorifier again, as you can see over towards the left-hand side of the screen. That's going to be typically supplied with self-acting valves that operate on that proportional control. And that's all well and good. That'll work efficiently. Because we've got that storage of hot water on the secondary side, it's far, far more stable. The release of energy across the heat exchanger is going to be more stable. But if we want to generate sources of hot water from steam instantaneously and on demand, then it's highly likely that we are going to need to increase the sophistication of the controls and move from a self-acting to a control valve that's going to have the P plus I or even the P plus I plus D control philosophy. So we can now bring all of those benefits together onto a fully packaged heat exchange solution to ensure that we get a very accurate and responsive control. So, for example, we can have a PLC panel, as you can see here, the heat exchanger package that's demonstrated in the middle of the screen, the various control valves, isolating valves, flow meters, steam traps. We can have a fully packaged solution that's easy to install and maintain that can bring a lot of benefits compared to a traditional shell and tube heat exchanger. And whilst sizing the plate pack or sizing the heat exchanger itself is critically important, by oversizing the plate pack, it means that we can allow a number of key benefits. It simply means that if we allow enough space in the heat exchanger for the condensate to sit there for a short period of time, it means we can allow for that condensate to give up as much of its heat energy as we possibly can. We can allow that condensate to cool to 100 degrees at 0 bar gauge, meaning we're using more and more of that useful latent heat energy, and meaning that we're taking as much of the sensible heat energy out of the condensate as we possibly can. The benefit being that regardless of the fall in pressure downstream of the steam trap, we're greatly minimizing, if not eliminating, any flash steam losses or flash steam inefficiencies. So we can actually move the control valve from controlling the steam entering the heat exchanger to controlling the temperature of the condensate leaving the plate pack. It's taking the place of the steam trap, if you like. And in many cases, we can add an extra 2 or 3% efficiency by simply controlling on the condensate side than we can by controlling on the steam side. So there are a number of factors that can also affect the rate of heat exchange. We've mentioned previously the presence of air. That insulating film of air can be the greatest inhibitor to heat transfer. And it also means that we can no longer rely on that pressure to temperature relationship. And that's really got its basis in understanding Dalton's law of partial pressures. Basically, any air that is present entrained within the steam means the steam will be supplied to the heat exchanger at the expected pressure, but it's simply going to have a lower temperature in it. We also know the benefits of keeping the steam as dry as we possibly can. The drier the steam, the more heat energy is going to be present in the steam, and the greater the rate of heat transfer is going to be. But another key benefit of drying the steam using a separator is by removing the moisture droplets, we're protecting the control valve from the risk of that erosion. So we know that one of the biggest problems that are faced by heat exchangers are that the control valves can be incorrectly sized. For example, if a control valve is oversized, it's going to spend a lot of its time operating very, very close to its seats. That's when erosion occurs. If we've missed off the conditioning ancillaries altogether, that's when erosion occurs, and that's when we're at risk of steam bypassing across the control valve onto the heat exchanger. So we either get an inefficiency from an energy perspective, maybe even the high limit valves and the relief valves pop in, or B, we get product spoilage. So a control valve should be sized in accordance with the mass flow requirement of the process. I just want to quickly go back to one of those basic thermodynamic equations that we can see above and to the left. This equation tells us how much energy there is in a mass of steam. So the Q value, that's the kilowatt rating, the energy content. M, that's the mass flow rate of steam. HFG, that's the enthalpy of evaporation or the latent heat. The dot, that basically denotes that the unit is a moving or a mass flow rate. So in other words, if we know the pressure of the steam going on to the heat exchanger, we know the latent heat. And moving across to the right of the screen, you can see that at 10 bar gauge, the enthalpy of evaporation, the latent heat, 2000 kilojoules per kilogram. So let's say that on this occasion, let's say we know the kilowatt rating of the heat exchanger. It's badged. And we need to know the mass flow rate of steam that is required to get the required heating effect. As we've mentioned, we can rearrange the equation to use what we do know to calculate what we don't know. For example, if we divide the 300 kilowatt by the 2000 latent heat energy, we get a mass flow rate of 0.15 kilograms per second, which works out at 540 kilograms per hour. So we've basically used that thermodynamic equation to calculate our steam demand and therefore to correctly size the control valve. But you remember that rule of thumb we also spoke about? Well, if we multiply that Q value, 300, by 1.8, we get 540. So it's the same. So another thing we need to give thought to is how dry the steam is. That really emphasizes how critically important that separator is. We know that wet steam results in mechanical issues such as erosion, corrosion, water hammer. But if we fail to put the full amount of energy into the steam to make it evaporate to produce dry saturated steam, we're going to end up with wet steam. And as we can see from the temperature enthalpy curve, that wet steam is going to have less energy contained within it. So you can appreciate that with wet steam, the process time is going to extend and extend. But if we add that to the presence of any air that could be entrained within the steam, then you can appreciate that insulating effect together with the lack of energy in the wet steam. It means that the energy going into the process is going to be greatly reduced and the process time is going to extend. So please use this information wisely, and you can understand and you can make more sense of this information by downloading that very, very useful little app that we've spoken about. And we know that when steam gives up its heat energy, it changes state to condensate. We need to get that condensate away from the process and away from the distribution network, utilizing the steam trap. And it's at this point that next fortnight's presentation on the topic of steam trapping will help to continue our journey. So I just want to summarize very, very quickly. It's the latent heat energy. It's the enthalpy of evaporation. That's the important number whenever we determine how we should be correctly sizing a heat exchanger. We know that steam gives up its heat energy by condensing. We know that the condensate doesn't have any value to the heat exchanger and therefore needs to be removed. And as with the previous presentation, we also know that keeping the steam as dry and free of air as possible is critically important. So in 2 weeks' time, we will continue with our journey, understanding steam trapping. For those of you that may have any appetite in undergoing a little bit more formal training, then we've got a number of training centres around the world that you may be able to attend. Here in the UK, we've got a dedicated website, so please do feel free to check that out if you've got any appetite in understanding a little bit more. So I'd like to thank you very much for taking the time to join us on today's presentation. If you do have any questions that have not already been addressed in the chat function, please feel free to put them there now. Otherwise, please feel free to reach out to me at any point on LinkedIn, and I'll be glad to answer any questions that may arise. So Brian, Steve, if there are any questions that may have been asked during today's presentation, please feel free to shout them out now.
Yeah, hello Dan. Thanks. Another great presentation there. Thank you very much indeed. We do have a couple of questions actually. If I could just put those to you on behalf of those that have raised them, if you wouldn't mind. Yeah. So the first one is just around plate heat exchangers. And the question is there any regular maintenance regime that needs to be adhered to with regards to steam plate heat exchangers?
Regular maintenance regime. Well, the control valve should require regular calibrating, stripping down to check the seals and so forth. The good news is that by observing the stroke on the control valve, it does give us some indication with regards to any wear that may be present. For example, if the control valve is opening wider and wider over a series of months, it's an indication that the plate pack may be becoming scaled up with debris, and therefore more and more steam is required to satisfy the process. So routine service and maintenance of the control valve itself, cleaning of the strainer, calibration of the flow meter, any steam trap that is located downstream of the heat exchanger itself should be regularly checked. But with regards to the plate pack itself, it's actually been optimized specifically for use on steam systems. So to a certain extent, it can be considered self-cleaning, providing we've got a reasonably good condition of steam.
Okay. So I guess that's where ensuring you've selected the right type of heat exchanger for the application becomes important as well then.
Absolutely.
Yeah.
Absolutely.
Okay. Excellent. All right. Lovely. Thank you. And there's another question here from Alan with regard to pressure control, pressure reduction, I guess really is what we're talking about. And it says, Dan, with using pressure to control the steam temperature, what happens when the steam goes through a pressure reducing valve? If the temperature is reduced, where does the excess heat energy go?
Yep, that's a very good question. We know that if we reduce the pressure, we reduce the temperature. But if you can imagine that temperature enthalpy curve that we looked at, we know in reality the steam is not going to be 100% dry. Let's say the steam is 92, 93% dry. There's a certain amount of moisture entrained within the steam, and because we've got slightly moist, slightly wet steam, we know that it's going to sit slightly to the side of the saturated steam curve. As we get a reduction in pressure, we get a slight release of energy, but that energy, it actually has a beneficial effect. It actually causes the steam to become dried. So it means that the steam will be dried and it will be brought up closer and closer towards the saturated steam line. So the energy isn't lost, it simply moves state. It dries the slightly moist steam.
So we're actually using that pressure reduction as a benefit to further dry the steam then in effect.
Absolutely. It's got a slight flash steam effect that is just getting rid of the moisture that would otherwise be entrained within the steam.
Okay, excellent. All right, good. And just finally, just your thoughts, actually. There were a couple of questions around a theme, just with regard to the use of steam, particularly around heating type applications, still heat exchange, obviously, but heating specifically, in sort of large buildings and in particular hospitals, and whether we see that still commonly in use or whether there's a change towards other solutions.
Absolutely. I mean, as we've mentioned, steam's a very efficient carrier of heat energy. For the reasons we've gone through, we don't pump it. It's got high heat content. We distribute it in a very small pipe diameter, all of which are hugely beneficial in applications such as hospitals. But we also know that if a hospital's also got other use for heat energy, for example, if they're using steam in the laundry, if they're using steam in the cooking facilities in the kitchen, if they're using steam for sterilization, a little bit of humidification, they've already got the steam plant on site. And it's really beneficial to ensure that we're using all of the excellent properties of steam that we've already discussed for the benefits for general heating and domestic hot water purposes.
And I guess that's going to change from one site to the next, depending on what their individual requirements are and the topography of the site and the infrastructure and everything
Absolutely.
else.
Every application and every site is going to have its own quirks, its own nuances. So it'd be very difficult to state what the advantages and what the drawbacks would be without having more information.
Yeah, for sure. Okay, that's lovely. Thank you. That concludes the questions. Thank you very much, Dan.
Thank you.
Okay, thanks, guys. So thank you to Spirax Sarco, Dan and Stephen. Thanks to Fiona and Nikki from the IMechE, and a big thank you to my colleagues at Project Solutions, which help us keep the show on the road. I'll see you in 2 weeks' time. Goodbye.
Thank you.
Thanks, everyone.